questions on what we've been doing so far? No questions? OK, so I think I forgot to say this last week. Just to kind of remind everyone that classes at UW are off on, well, for this class, it'll be February 22nd. And just to confirm, somebody asked about this, just to confirm that actually there will not be class here as well. OK, so then what I want to talk about today is fault tolerance, where we've started to talk about fault tolerance last week with talking about the basic model and transversal gates. And so now I want to kind of define for you more rigorously exactly what a fault tolerant gadget is, and then show you a kind of the more full range of fault tolerant gadgets. Although I don't think we'll get the complete set of universal set of fault tolerant gadgets until next week. There, good, Chuck. OK. So, right. So what does it mean to have a fault tolerant gadget? Well, remember there's kind of two properties that we're trying to achieve, which I kind of alluded to last week, and I'm going to make more precise now. So first of all, we want it to do the right thing, right? It has to be an encoding of the original gate or location that we're trying to implement. And the second is that it needs to keep error propagation under control, right? We want to avoid that case where you have one gate that can have a fault and then give you two errors in the same block of the code, right? So again, the underlying idea there is that we're now thinking about errors occurring kind of independently with each location, say with probability p per location. And we want that, as with an error correcting code, we want that the logical state, the logical computation that's encoded, have errors at only order p squared or something lower than that, right? And so we want there to have a situation where you have to have two faults, at least two faults close to each other, in order to cause a problem. Again, in a very big circuit, there will certainly be 2 faults and 3 faults and 4 faults, many, many faults. But if they're spread out, then our error correcting code, and by doing error correction ever so often, we can avoid having situations where there's many at once, or many that kind of build up over time and cause a problem that we can't correct. OK, so how are we going to define rigorously when a gadget satisfies these two properties? Well, in order to do that, if you think about it, we need to talk about two things. So one, we have to talk about how many errors there are in the state, right? Which is actually not completely trivial to define. And so we're going to do that. And the second thing we need to talk about is what is the logical state, which is, again, not completely trivial to define, particularly for a state that has some errors, right? But I mean, they still are fairly intuitive. And it's your first stab, you can write down something that's pretty close. And so we just have to kind of firm up those intuitions as to what these things mean. And so to do that, we're going to use two kind of hypothetical operations. So these are not operations that you'd actually be able to implement. And so one of them is called an R filter. And so an R filter is going to encapsulate this idea that a state has R errors. It's actually going to be R or fewer errors. So it's a projector onto the subspace spanned by the quantum error correcting code. And let's say with with up to R Pauli errors on it. Okay? So the error correcting code is some 2 to the k dimensional subspace. And for each error, that maps you to some other subspace, which, if the error is in the stabilizer, it's the same subspace. But if it's not, then it's mapping you to some other subspace. And we're looking at the thing that's spanned by all of these possibilities. So even though we just have Pauli errors, of course, since we have taking the span, we can have addition of these things, and so we can actually have any weight R error, or really any R qubit error. Okay? And so this subspace definitely contains all the states that we can get to with a code word that has up to R errors on it, right? And in fact, so if you're restricted to act to R specific qubits, then there'll be some things that are superpositions of errors on different qubits that might be hard to actually have an error that gets to. But if you want to have a linear space, this is what you have to work with. And so I should say that we're going to fix here some quantum error correcting code. And for later purposes, we'll say that this thing corrects up to T errors. Okay, that's not really relevant to the definition of an R filter, but it will be important in a little bit. And so I'm gonna refer to this R filter using a graphical notation. So let's write it this way. So the R is the parameter of how many errors it's filtering. And the line here is supposed to represent a block of the quantum error correcting code. The quantum error correcting code is going to be in green. Okay, and so how does this represent having R errors? Well, if you have a state that passes through this filter, so you have a state that comes in, and then you do this filter, the thing that comes out has at most R errors. Okay, and the way we're going to use that in practice is we're going to say that the state that's coming out of some other kind of circuit is equal to the same thing followed by an R filter. Okay, you'll see that in a minute. Okay, so the other thing we need to do in order to encapsulate the notion of what the encoded state is define an ideal decoder. So the ideal decoder takes the block of the quantum error correcting code, and it corrects errors perfectly according to the usual error correcting procedure. And then outputs a logical state. So this is a procedure, of course, that you can do in principle, but what you can't do is do it without any errors. And the ideal decoder doesn't have any errors in it, by definition. Okay? So if you try to do this in practice, you'd always have some possibility of errors, and that's why this is just a hypothetical thing. Yeah?
Do you mean in the sense that you decode the maximum likelihood of the error occurring? Like if it's a lower weight error, we assume it's likely to be a lower weight error.
Yeah, so right now we're dealing with an error correcting code that corrects T errors. And so you just use whatever error correction procedure that accomplishes that. Now you start to get some ambiguity if you have an error correction code that can sometimes correct more than T errors, but only some some errors of higher weight. So for instance, like the 7-qubit code, you can correct arbitrary single-qubit errors, but you can also correct an x-qubit error and a z-qubit error on separate qubits. An x error and a z error on separate qubits. So that's like a 2-qubit error that you can correct. But you could say, well, actually, I'd rather correct an x error and a y error on separate qubits. And that's a little trickier, but you can do that as well, I believe. Is that right? Yeah, it must be right. OK. And so that would be a different decoding procedure. And then you kind of have to pick one. And usually it makes sense to just pick whatever decoding procedure you're using in your protocol.
So it's ideal that given the symptom, it knows what the right error to correct is.
Yeah. So an error correction procedure, you can basically boil it down to a map from synchromes to errors, and we're just doing that, but we're also measuring the synchrome perfectly. We're not. That's the important part here. That we're measuring the synchrome perfectly, and then we're doing this decoding procedure perfectly. Neither of which you could do in the actual system. Okay. And so I'm going to draw this way. So now I'm having compunctions. Can you tell the difference between the green and the white here? Is that clear enough? I was wondering if I could change colors.
Could you do a different color?
Yeah, let's try that.
We already have white text.
Huh?
We already have white letters on the board.
Oh, different than the white, you think?
Yeah.
I could do that. I don't think that's the problem. But I'm mostly worried about the contrast between the white and the green.
Yeah, a little bit.
How about purple? Is that clear enough? Tell the difference? OK. Anyway, so the purple is going to represent a decoded logical qubit, and the purple things are going to be ideal, so they don't have any errors on them anymore. Okay, whereas the green qubits are part of the real system, and therefore that they have errors occurring according to whatever our error model is. The green ones are not qubits, I should say. They're blocks of qubits, right? They're n qubits. Okay, and so the ideal decoder, hopefully you can see how this encapsulates the idea of the encoded state, the logical state of the system at a given time. You take whatever you have and you stick it through the ideal decoder, and then what comes out, that's the value of the encoded state. Okay? Okay, so then in order to define gadgets, I'm going to use define fault-tolerant for gadgets. I'm going to use pictures based on these things. And so to do that, I'm going to need pictures for the different kinds of gadgets. So, so we have gates. So this is the encoded version. And then I'm going to put an S there, because that has up to S faults. And then the ideal gate looks like this. Okay, circle with, and there's no S because there's no errors in this. And then we have, so this is a 1-qubit gate. You could also have a 2-qubit one. Which would look like this. Okay. And then we have state preparation location. And that's going to look like this. And again, it could have S faults. And the ideal one looks like this. we have measurement locations. So the symmetric thing. And then finally, so this is kind of the main, the types of locations that we're going to deal with. But the other kind of gadget we need to have in the fault-tolerant protocol is an error correction gadget. So that looks like that, a rectangle, and I'm going to write EC in it. And again, it can have S faults. But there's no ideal version of this, right? Because the ideal thing, the code is gone, and we don't have any errors anyway, so we don't need that. So if you wanted to draw an ideal equivalent, it would just be a line, a purple line. OK? So that's the graphical language that I'm going to be using. Now I have to keep all of these. And so let's define our two properties for gate gadgets. So this is going to be the GPP, the gate propagation, error propagation property. So it's satisfied if for all Rs such that R plus S less than or equal to T. So, so the idea here is it's a property that limits how much errors propagate in the system. Okay? So there's two parameters, R and S. So R is going to be the number of errors in the state coming into the gate gadget. And then S is going to be the number of faults in the gate gadget. And I want to make sure that they don't add up too much. So it looks like this. So the state that's coming in has at most R errors. It passes through an R filter. And then it goes through a gate gadget with S faults. And that is supposed to be equal to the same thing, but then passing through an R plus S filter. Okay? Does that make sense? So this is an example of what I said, of how we want to say this state has at most R plus S errors. How do we do that? Well, we do it by saying that it's equal to the same thing passing through an R plus S filter. Adding this projector doesn't change anything because the state already would pass that test. Okay? So this is for one qubit gate, or really a gate that acts on just one block of the code. So if you have a 2-qubit gate or a 2-block gate, it looks like this. So now we have 2 blocks that are coming in. And so each one of them could have a separate, R1 and R2 errors in them. And then we do our gate gadget, which has S faults. And the thing that comes out, oh, sorry, too soon. And so the state that comes out is supposed to have, well, okay, let me rewrite this first, and then we can discuss what it's supposed to be. So we're going to have to put a filter on each of these. And what should those filters be? Well, if you think about the C naught, and the transversal C naught in particular, it propagated errors from the first block into the second block, and from the second block into the first block. So we can't avoid adding together R1 and R2, right? At least if we want the transversal to be an acceptable thing. And I'm not sure there's any way to do it if you didn't have that. And then, of course, we can add in any faults that happen during the gate itself. So what this should be is R1 plus R2 plus S. And this down here is R1 plus R2 plus S. Okay. And again, we only require that this be true if R1 plus R2 plus S is less than or equal to T. I mean, in many cases, it will be satisfied even if those greater than T. But in the case where we have that many errors, we don't really care that much anymore, right? It's just everything is lost anyway. It's not going to work right. So, I mean, there may be certain circumstances where you actually want that to be true, even when this is not satisfied. But that would then be a stronger version of this property. OK. So does that make sense, that property? Yeah.
So is it correct to say that whenever a location doesn't do what it's supposed to do, then you have an error? Is that how the R and S are counted?
Yeah. So remember, So R is just some number we put in to test these properties. Okay. And it doesn't talk about locations at all. It's just take the state and it passes through this projector.
But you still have to define the R errors that occur.
No, you don't. You see, because the R filter is defined as the projector onto all possible R errors, or it's sufficient to look at all poly errors up to weight R. Okay. Now, so the S is defined in accordance with this basic model that we talked about last week, where each location is either perfect, which happens with some reasonable probability, or with some other probability in the independent model anyway. It's not perfect. It could do anything, and that we call a fault. Okay, so we're just counting the number of faults that occurred, given the actual probability distribution of that occurred for the computation.
So what about, for example, in your state prep, then you're preparing multiple qubits. Some of them goes wrong. You count that as one location, multiple locations.
We can talk about that when I get to state preparation. Okay. So, but remember that what we're counting. So this is S faulty physical locations. Okay. And so if it's a 2-qubit gate, then when a 2-qubit gate, so if it's a 1-qubit gate, when that location is bad, it's just that 1 qubit that gets an error. But if it's a 2-qubit gate, it could be both qubits involved in the gate that get an error when the 2-qubit location is faulty. And that's the 2-qubit location, right? Not the 2-qubit logical gate. Those are separate things. Okay. So to be a little bit more specific, each of these things is a completely positive map, albeit not a trace-preserving map because they involve projectors. Okay. And there are some faults in here. And the faults on this side should be the same faults, right? So they're in the same locations, and the gates do the same thing, okay? And then I'm saying that these things are equal as CP maps. Yeah. Okay. Okay. So then. The next thing is the GCP, the gate correctness property. And that's satisfied So now we're going to use the ideal decoder to define what happens. And what we want to say is we want to say that the logical state gets transformed according to the right logical gate. So what does that mean? Well, we can write it this way. So again, there's going to be a separate version for the 1-qubit gate and the 2-qubit gate. So suppose we have a state, an error-correcting code. It has at most R errors in it. We do this gate with S faults, and then we decode it. So this is supposed to be equal to the same thing. Well, not really the same thing. We put it through our filter, and then we decode right away. And then we do the corresponding logical gate on the decoded state. Okay? So you can see how this corresponds to this fault-tolerant gate doing the right thing, right? This is the state that we started out with at the beginning after the filter. And then this is this state, sorry, this is the logical state that we get started out at the beginning. We started with this physical state, we decoded it right away. So this is the logical state at the beginning, and then we did this gate. And that's supposed to be the same as if we did the whole thing and then decoded. Right? So the logical state is changing in just the way we intended. Okay? And again, this is true, or we only insist that it be true if R plus S is less than or equal to T. Okay? And then similarly for the 2-qubit gate. Again, we have two blocks coming in. We do a gate, and then we do the ideal decoder on both of them. This is supposed to be equal to if we decoded right away. Okay. So you might ask, why do we need these filters in front? Right? Couldn't we just write these things down without the filters? And the problem is that in that case, we wouldn't expect this property to be true, right? Because suppose you have a state that has, let's say we're dealing with a code that corrects one error. You have a state that comes in and it already has an error on it. And then before you do anything, you do this gate, this fault-tolerant gate gadget, and it has another fault. Okay? Now the state has two errors on it, and when you decode it, you'll have an error. Right? Whereas if you decode it right away, you'd get rid of that first error, and then you're doing this ideal gate. Okay? So in the first case, where we didn't decode until the end, we've accumulated two single-qubit errors that added up to a logical error. In the second case, we don't have a logical error, right? So that wouldn't be true. But nevertheless, we still want this situation to be acceptable. That if the state that comes in doesn't have too many errors, and that between that and the new faults occurring in the gate, that's something that's still correctable, then we want it to work. Okay? So whereas the error propagation property often will still be true even if this is not satisfied, you don't expect that to be true of the gate correctness property. I mean, it can be in very specific cases for specific arrangements of errors and faults, but in general, it won't be. Yeah?
Sorry, could you repeat that again?
Yeah. So suppose you have a code that corrects one error, and you have a situation where the state that's coming in has one error in it, and then you have a gate gadget that has one fault in it. Right? That fault can cause a second error. And so now you have two qubits that are wrong, and that's something that's uncorrectable. Okay? So you don't expect this to be true if R plus S is greater than T.
Okay, okay.
Whereas this one might or might not be true. Okay? Yeah, so this tells you, if you have a gate gadget, how to check it to see if it's fault tolerant or not. You check these properties and see if they're satisfied. And in principle, that might require going through all possible errors on the input state. Well, first of all, you might have to change R and S, right? So even if t is 1, well, first of all, you have to look R equals S equals 0. So when there's no errors, it should definitely work right. But you also have to look at R equals 1, and then try all the possible errors there, and S equals 0. And then you have to try R equals 0, so the input state is right, but then S equals 1, and look at all possible faults. Okay. It's a bit simpler. It's sufficient to check just Pauli faults and Pauli errors. And the reason for that is the same linearity argument, basically, that we gave when we were talking about error-correcting codes, right? We said it's enough to have an error-correcting code that corrects Pauli errors, because anything else can be written as a superposition of them. Okay? So the same thing applies here. And in fact, that linearity means that it actually holds even for much more general error models and this kind of independent things that I mentioned last week. Yeah?
I have a question regarding, let's say, 2-qubit gate and this gate correctness property. Mm-hmm. So if the input is, so the 2 qubits, if there's some errors in them,
right.
1 or 2.
Yeah.
Let's say there's 2 sets of errors that would give the same syndrome. But then our ideal decoder can still somehow figure out what the correct logical output should be.
Sorry. So you mean that this block and this block have errors with the same syndrome?
Oh, no. I mean, it's conceivable that there's 2 sets of errors on, let's say...
So it's not really specific to the 2-qubit block, then.
Okay.
Because in general, you have, in this situation, you have 2 possible sets of errors that have the same syndrome.
Right. Does our ideal decoder know to give the...
Yeah, OK. So let's think about this. So if let's think about it in the context of stabilizer codes. It's a bit easier. So you have 2 errors that have the same syndrome. OK? That's certainly possible. That happens all the time. But that means that your syndrome can't, that means that they're in the same coset of n of s in the Pauli group. Okay? And in particular, they have to differ by an element of n of s. Right? Remember, that's what it means to have the same syndrome, essentially. That they commute with the same subset of things in the stabilizer, and therefore their product has to commute with everything in the stabilizer, and so it's an n of s. Okay? So error 1 and error 2 differ by an element of n of s. Now, if that element of n of s is actually an element of the stabilizer, then that means that error 1 and error 2 actually create the same state when you apply them to a code word. Okay? And so, so the ideal decoder will it doesn't have to figure out which one it is. It just picks one and decodes, and you get the same thing, no matter which one you pick, right? Because they do the same thing to the code word. But now let's suppose the opposite situation, where it's not an S, but it is still an n of s, the difference. Well, what that means is that these 2 things have the same syndrome, but they also have different logical states associated with them. Okay? And so if you pick one, you'll get one logical state. If you pick the other, you'll get the other logical state. But see, that's the case where you can't correct both of these errors, right? Because then you're saying that E1 dagger E2 is in n of s minus s, right? So that's exactly the situation where you can't correct. Okay? And this is why. Because your ideal decoder can't distinguish these 2 errors.
So we can't make like an equivalence between the gate correctness property for that circuit to be like, say, an ideal line and a gate and the ideal output. So
right, that's a little more subtle. You mean on the right-hand side? You're wondering why not?
This is not equivalent to, let's say, an ideal input.
Right. Yeah. So, but actually, there's a little more subtle reason for that, which is so this thing, as I said, is a completely positive map. But that means that you can put anything in as the input. Suppose as the input you put in something that has more than r errors, r plus 1 errors. Well, then this thing will annihilate it. You'll just get 0. And I don't mean the ket 0. I mean you'll get nothing as the output, right? Because it's not trace preserving. That can never happen. The projector will kill it. Okay? And if you don't have this projector here, and you just immediately put in the ideal decoder, then the ideal decoder doesn't know that it's supposed to kill it. It'll correct the errors. Okay? And you'll get some output state. And you won't get nothing out. You'll get something out. Okay? And so then they wouldn't be equal. Right? So that's the real reason why we need to keep this projector here on the right side is to kind of, so the fact of this projector, you can put in anything, but this filters out and keeps only the part of your input that has R errors. And so we need to do that on the right-hand side too. Okay? Okay. So, right. So, okay. So, so then we say that a gate gadget is fault tolerant. Maybe I'll just stick this in at the top. Gadget is fault tolerant. Sorry. So yeah, this is easy to get wrong. So when fault tolerant is used as an adjective like this, it does not have a hyphen. But if you say a fault tolerant gate, then it does have a hyphen. That's you know, funny rules of English. But okay. So gate gadget is fault tolerant if it satisfies these two properties. Okay. And so according to this definition, transversal gates that we talked about last week are fault tolerant. Okay, and let's see why, right? So, so remember, transversal gate, you're lining up the ith qubit of the first block with the ith qubit of the second block. And so if you guys have a one, well, let's do the 2-qubit gate, because that's more interesting. Okay, so now if you start out with R1 errors on the first block and R2 errors on the second block, well, these R1 errors can propagate to the second block and to the corresponding R1 qubits. And the R2 errors on the second block can propagate to the first block and the corresponding R2 qubits. And moreover, every time we have a fault, that could be a gate that's affecting both the first block and the second block. Okay, so it could be adding an error on each of those blocks. But that means the first block still has, at most, R1 plus R2 plus S errors, right? The R1 it started with, R2 that propagated from the bottom, and S new ones. And similarly for the second block. Okay? So it satisfies this definition. And so what about this definition? Well, if R1 plus R2, so yeah, so I could say, so the transversal gate is an example where you don't need this condition, right? It's true whether R1 plus R2 plus S is less than or equal to T or not. Still true if it's arbitrarily large. But of course, this one does require that, as I said. And so let's think about it in this case. So, so we have all these errors accumulating, as we've just said, but each block could have up to R1 plus R2 plus S, which is less than or equal to T. And therefore, each block, it's still a correctable error. Right? So assuming that we came up with a gate that acts the way it's supposed to on the code words, if we decode afterwards, we'll get some logical thing. If we decode before, we'll get the same logical thing, and then we do the same gate. Right? So it's easier if you write it down, I think. But because these errors are correctable, we never at any step get something that's not correctable, and therefore this gate gadget acts the way it's supposed to. Okay. Okay. So okay, so let's then move on to other kinds of locations. So what does this look like for state preparation? So this is the error, the state preparation error propagation property. And so what does that look like? So we have our preparation gadget with S faults. And this is supposed to be equal to the same preparation gadget with S faults followed by an S filter. And we want this to be true if S is less than or equal to T. Okay? So this is different from the gate thing in that we don't have this initial filter. Why not? Well, it's a state preparation thing. There is no initial state. We're just creating a state, right? So there's no initial thing that could have errors in it. All we care about is the faults that actually occur during the preparation step. Okay? And then the PCP, preparation correctness property, so that's satisfied if, well, we take the state that we prepare and stick it through an ideal decoder. And this is supposed to be equal to the state we would have gotten if we just prepared it in an ideal way. Okay? That's a pretty simple one. Yeah?
So what exactly is PPP saying? Because doesn't the preparation with the S indicate that we already have at most S errors? So what is...
No. So what this is saying is that this thing here on this side says that we had a preparation procedure that has at most S faults. Okay? But, and then what the property is saying is that the state that comes out of that procedure has at most S errors. This will be, we'll discuss this sort of thing a little bit more later, but the basic idea is that in order, I mean, so transversal gates that control error propagation very easily. But for state preparation, we're going to have to go beyond transversal gates. And suppose you just said, OK, I want to make an encoded 0 state, and just write down some circuit that creates the encoded 0 state. Well, that'll involve non-transversal gates. It'll involve C0 gates to make this error-correcting code between different qubits of the code. And if one of those C0s has a fault, then in general, well, it will certainly affect the 2 qubits that it's touching, but then those can be propagated even further by later on C0s. And so you could get many, many errors in the code block out of just one fault. Okay, and that's what we want to say should not happen with this property. Yeah, so it's not really a propagation property because there's nothing to propagate, but it is kind of a propagation property because it's talking about propagation inside the circuit. Okay? And then, of course, we say that a state preparation gadget is fault tolerant if it satisfies both of these. So measurement is going to be a bit different in one sense. It's not going to have a propagation property at all. Why is that? Well, the propagation properties all tell us how many errors there are on the output state. But a measurement gadget has no output state. Well, it has a classical output. But we're assuming the classical things don't have errors. We don't care about the errors anymore. So we only have to talk about the measurement correctness property. OK, and I'm realizing I forgot to write S less than or equal to T here. Again, this is important for the correctness property. It may or may not be relevant for the preparation property. OK, so the measurement correctness property is satisfied if, well, so now we do have an input state. So we want to put a filter on it. and then we do a measurement that has S faults. And maybe it's worth using yet another color for classical bits that come out, just to make it clearer. Okay, so we do this, we get some classical bits out, and this is supposed to be equal to the state if we take the thing after the filter and immediately decode it, and then do an ideal measurement on it. Okay? And again, this should be true if R plus S is less than or equal to T. Okay? Does that make sense? Yeah.
For the ideal measurement, is that like do we think of it as like we know exactly what the state is after one measurement, like
No.
Or
no. So it means the measurement implemented as a regular quantum measurement, but without any errors. Okay. So if this is a gadget for a z-basis measurement, then this does the z-basis measurement on the single qubit that we have here. I mean, it's not really relying on being a single qubit. It could be multiple qubits, whatever. But it does the same measurement. It's just, it does it without errors. That's the same. Okay? Now, there was a question before about state preparation. Something about multiple qubits. You want to repeat that question, or if you figured it out?
So multiple qubits, for example, if you're preparing an encoded state, errors occur on like some number of qubits. Do you consider that preparation as one location or multiple locations?
Okay, so you're imagining a code with one logical qubit in it, and so you do some circuit that does this state preparation that creates this encoded state.
Okay, so
and again, each physical gate corresponds to one location. I mean, the ideal circuit that you're imitating, that you're corresponding to, is just one location, right? It's a preparation location. But the physical thing will have many physical, the actual implementation, the gadget will have many physical locations. Okay? Yeah.
On the assumption that R plus S is less than or equal to T, does we include the case that an error from the gate cancel and income?
Yeah, that's right. So the point is this could be true for arbitrary sets of R errors and S faults. But there will be some cases where you have the incoming errors and you have faults that produce errors that just cancel them out, or in part or in whole. It will still work then, right? It will act like there's fewer errors, basically. But in cases like that, you certainly will have some examples where R plus S is greater than T, but it still works because you have cancellation or because the code is actually able to correct a few more errors in certain cases, or whatever reason. Or maybe the errors don't cancel out. You get a logical error, but then you get another logical error that does cancel it out, right? So there's lots of possibilities. The main thing, but the thing is that once R plus S becomes greater than T, then we just don't really know. Sometimes it might work, sometimes it might not work. But when R plus S is less than or equal to T, there's not too many errors, and it should work right then. That's the important thing. Okay? Other questions? Okay, so then the last kind of gadget is the error correction gadget. And so those properties are a little bit different. So first we have the ECRP. So this is the error correction recovery property. And it's satisfied. Why do I keep doing that? So what does this look like?
Oh,
yeah.
Just one question regarding the last property again.
Yeah.
Measurement correctness property. For the first one, it implies that we get the number of errors in that is still less than t. I understand that, but once you perform the measurement, so then implicitly it's saying that we have a classical decoder which could also decode, translate from the classical measurement to the right classical measurement.
Yeah. So the so the assumption is that a measurement gadget, whether fault tolerant or not, is going to take a code word that comes in, or a state that's encoded in the code and might have some errors on it, and do some measurement and output decoded classical bits.
Mm-hmm.
Okay. And the reason we want to make that assumption is because we're assuming that the classical bits are perfect and we're not using an error correcting code at all for them.
Right. But this is saying that the classical information afterward can be converted to the ideal classical.
No. So what I'm saying is that the classical information afterwards is the same, or the same distribution, as the ideal classical information. Because the classical information on the left-hand side is already not encoded. The real measurement gadget is already decoding it.
Okay.
That's what I'm saying. Okay. And so we just want to make sure that any errors in that measurement process, which can only occur in the qubit part of the process, are not going to mess up that output.
So there's an implicit decoder in that.
Yeah.
In measurement. Okay.
Yeah. It depends. I mean, once we start to talk about specific measurement gadgets, you'll see that the decoder can be pretty implicit in some cases, in that you don't necessarily see it at all.
Oh.
But that's sort of true. There's always going to be some form of decoder in there. It's true, but you don't have to do a full decoder for the quantum code word. That's fair to say.
Oh.
Okay, so the error correction recovery property is satisfied if this holds. So we have our error correction gadget with S faults, and that should be equal to the error correction gadget passing through an S filter. And this should be true for S less than or equal to T. Okay, so this looks like a propagation property, except that it doesn't have the filters at the beginning. Why is that? Well, the whole point of the error correction procedure is to correct errors. Okay? And so what we want the ECRP to do is it's saying that no matter what state we put in, even if it has lots and lots of errors, the state we get out should have at most S errors, which are due to the faults that occurred during the error correction thing. Now, you could definitely come up with a weaker version of this that had a filter at the beginning. And that said, it only works if the state you're putting in doesn't have too many errors. Okay? But this is saying whatever we get out, it might not be the right logical state. That'll be the next property. But the state that we get out should not have too many errors in it. Okay? Okay? And then we do have a correctness property. So this is satisfied if, and I'm guessing you could probably write it down at this point because it's going to be what you expect. So we have an R filter now, and then an EC with S faults. Then we do an ideal decoder. And this is equal to what we would get if we did the R filter and then the ideal decoder, and then nothing, right? Because the error correction procedure is not supposed to change the logical state. And again, this is for R plus S less than or equal to T. Okay? So whereas before up here I said that you could put any state in and the thing that comes out has not too many errors. Now I do want to make the constraint on the thing that comes in, because if it has lots and lots of errors, then it may be that the logical state I get out might not be right. Now, but there is a subtlety here, right? So what I'm saying here is not that the state is correct in an absolute sense. Although I guess I kind of am saying that. But I don't know what the correct state is in the absolute sense, because the thing that's coming in might have already had a logical error at some point in the past. Okay? All I'm saying is that the state that comes out after the error correction is the same as the state that I would get before the error correction. Okay? And that can occur when R plus S is greater than T, because, again, suppose you had this situation where you have a code that corrects one error. You have one error before and one fault during. And those could accumulate to cause a logical error before you get around to correcting the errors. Right? And then you're out of luck, the state that comes out has a logical error. But it has more to the point, it has a logical error that's not present on this side. If it had a logical error due to many errors before, then it'll be present on both sides, and this is fine, still satisfied. So you want to make sure the error correction doesn't introduce a new logical error. Yeah?
You don't need any relation between R and S for this to be satisfied.
This is the relation, that they should just add up to not be too much. That's right. The point is that, I mean, essentially this is a kind of an inverse relation, right, in the sense that if R is big, then S has to be small. So in that sense, there is an actual connection between them. But, I mean, if the error correction procedure has no faults, that's great. That's the best, right? Then it definitely should be correcting the errors. So it certainly doesn't, they don't need to, grow with each other or anything like that. Okay? Okay. So these are my definitions of fault-tolerant gadgets. And again, you can say a state preparation gadget is fault-tolerant if it satisfies the PCP and the PPP. Measurement gadget is fault-tolerant if it satisfies the MCP. An error correction gadget is fault-tolerant if it satisfies the ECRP and the ECCP. Okay? Yeah, so are there any questions about that? And before I start talking about how to actually implement gadgets that have these properties. No? Okay. So unfortunately, coming up with gadgets, fault-tolerant gadgets for state preparation and for measurement and for error correction are all a bit complicated, because just using transversal gates, well, it works in certain cases, actually. for measurement, but state preparation certainly requires more complicated things. And error correction is going to be more complicated as well. And moreover, all three of them are kind of intertwined with each other. Now we have to use tricks from one to make the others work. So I'm going to kind of build these up together. And I'm going to start out with what I think is the conceptually simplest procedure, but and also quite general. But and then we'll specialize if we have time today to other cases. Okay, so let's start with gadgets to measure physical Pauli operators, right? So think of this as a component of an error correction gadget. So for a stabilizer code, we want to do error correction by measuring the eigenvalues of the generators of the Paulis, right? So we want to measure a bunch of different Pauli operators. So the generator is a stabilizer. So we want to measure a bunch of different Pauli operators. So let's start out by figuring out how to measure one, right? And actually, I never really showed you this before in the error correction procedure, in the pre-fault tolerant part, right? So how do we do it in the absence of errors? Measure the eigenvalue of the general Pauli. So here's a very general way. So we have some code block here. And let's say it's a 5-qubit code. We want to measure eigenvalue of x, z, z, x, I, right, which is the first Pauli. So what we're going to do is we're going to use an ancilla, and we're going to put it in the state plus. And then we're going to do controlled Paulis. Here, I'll just write it this way. It'll be x, z, z, x, I. Okay, so you can also write this as 5 separate controlled Paulis. A controlled x, which is a controlled not, a controlled z, which is a controlled phase gate, and then another controlled z, another controlled x. So it's actually 4, I should say, Paulis. The last one, controlled I, is nothing. Okay? But the point is, I want to write it this way because then you can see where this whole Pauli is coming from. And so what does this do? Well, suppose the state is in a +1 eigenstate of this operator. Well, then when this is 0, nothing happens. When this is 1, we do this controlled Pauli, and we get a +1. So again, nothing happens. And the state that comes out is a plus. But now suppose it's a -1 eigenstate of this Pauli. So when it's a 0, nothing happens. But when it's a 1, well, we apply this Pauli, and it's a -1 eigenstate, so we get a phase of -1. So the 1 ancilla gets a -1 phase. And so the ancilla is now in the minus state. So if we take this ancilla and then do a Hadamard, and then measure, the state that comes out will be 0 for +1 eigenstate, and it'll be 1 for -1 eigenstate. Okay? And so we've done exactly what we wanted to. We measured the eigenvalue of this Pauli. Okay? So you can see how you can generalize this for any Pauli, right? You just stick the appropriate n-qubit Pauli in this block instead. And I should say that controlled x, controlled y, controlled z, those are all Clifford group operations. So this is just a Clifford group circuit. Okay, but now let's think about fault tolerance. So there's 2 things that make this a non-fault tolerant circuit. So the first one, I mean, I've drawn this as one thing, but if you break it up, it's, as I said, 4 separate gates. And suppose you do 2 of them, and then you have a fault, right? On, let's say, a bit flip on the ancilla, okay? Well, that bit flip will propagate forwards along these 2-qubit gates and create bit flip errors or phase flip errors, some other kinds of Pauli errors down here. And so now we'll have 2 errors in the code block out of 1 fault. Okay, so that's a violation of one of these propagation properties. I mean, obviously, if we're doing measurement, we don't have to worry about that if it's part of a measurement gadget. But if it's part of this, say, this error correction gadget, that's a problem. Okay? OK, so and then the other problem is that there's just one ancilla qubit here. And suppose it has an error here. Suppose it starts in the minus state. Suppose the Hadamard has a fault. Well, then the output that we get here will be wrong. Right? We'll get a 1 when it's a +1 eigenstate and a 0 when it's a -1 eigenstate. And we'll have the wrong idea about the output. Okay? And that'll violate, well, if we're doing the measurement thing, that'll violate that condition definitely, right? Because it's not doing the right measurement. Okay, that's independent from this issue about errors propagating. Okay, so in order to make this fault tolerant, we're going to take this idea, but we're going to have to change the gadget that we're using. So we're going to change the ancilla first. And so what we want to do is we want to try to use this idea of transversal gates. So instead of having multiple 2-qubit gates with the same control and different targets, we're gonna have multiple ancilla qubits, and then we're gonna do one gate from the first ancilla to the first qubit, and a gate from the second ancilla to the second qubit, and a gate from the third qubit ancilla qubit to the third. Oops. Got that wrong. And the fourth to the fourth. OK. So this is what we're going to do instead. But you see there's already a problem here. Because what we wanted up here is if this was 0, we did nothing. And if this was 1, we did all of them. OK? Well, now we have separate qubits. So how do we arrange that we do all of them at once? Well, the answer is to use an entangled state. So this state here is going to be this cat state, 0, 0, 0 plus 1, 1, 1, 1. OK? Yeah. OK. So so now, if we have the 0 branch, then we don't do any of these. If we have the 1 branch, then we do all of them. OK? So in that sense, it's kind of like this circuit. But now the state that we get out here, if it's a +1 eigenstate, will be the same cat state, 0, 0, 0, 0 plus 1, 1, 1, 1, 1. Sorry, 1, 1, 1, 1. And if we have a -1 eigenstate, we'll have 0, 0, 0, 0 minus 1, 1, 1, 1. OK? And so then what we need to do is we need to do a measurement here that will distinguish between those two things. OK? Now, again, we want to be careful because we don't want to well, OK. So the easiest way to do that, it turns out, is rather than do some C-naughts between these things, which could potentially create problems of its own, although I guess it doesn't actually. It's sufficient, it turns out, to do Hadamards on all of these and then measure. Why is that? Well, if you work out what the Hadamard does to 4 Hadamards due to 0, 0, 0 plus 1, 1, 1, 1, turns out that it's a sum over even x strings. And if you do minus, then it's the sum over odd x. OK, so what we're going to do is we're going to take these outputs and we'll take the parity. And if it's even, we know it's a +1 eigenvalue. If it's odd, it's a -1 eigenvalue. OK? OK, so has this solved the problem? Well, it definitely hasn't solved both problems. but it at least makes the propagation situation better, right? Because now if we have a fault somewhere in the middle here, say it's on this gate here, well, then this ancilla qubit could be wrong, this qubit in the code block could be wrong, this data qubit could be wrong. But this one down here is not affected, right? There's no continued propagation. So down here, if we have one error up here, we'll only get one faulty gate. One of these 4 gates faulty is only going to be 1 qubit that's affected here. Okay, so that's good. But we do still have some other problems. So for instance, one error here can flip one measurement output bit here. And then instead of even, we have odd. Right? You can do that with just a 1-bit thing. And so even just a single qubit error can give us the wrong measurement outcome. That's bad. But the other thing is I've actually hidden another possible source of errors, which is by saying this input state is this cat state. How do we make that cat state? Well, using some non-transversal gates. So what's a natural way to make the cat state? Well, you start with zeros. And then one thing you might do, well, it turns out, let's do it this way, is do the Hadamard on one of them. So it's 0 plus 1. And then you do C naughts. To the other qubits. Okay, let me just modify this slightly to be a little bit more efficient. Okay? So if you look at this, this will make a cat state. Right? This goes 0 plus 1, and then if it's 0, nothing happens here, and you get all zeros. If it's 1, it flips all the other 3 bits. Okay, and so you get 1, 1, 1, 1. Okay? But the problem with this is that, again, it has these non-transversal gates. And if one of them goes wrong, you could have multiple errors. So in particular, suppose this gate here has a fault, as an example. Then you could get a bit flip down here, and then it propagates down here, and then these 2 qubits are both flipped. And then you'd have 0, 0, 1, 1 plus 1, 1, 0, 0. Right? And then if you have 2-bit flip errors in here, well, then that does propagate to 2 qubits in the code block, which is a problem. Yeah, OK. So how do we avoid that? Right? Well, what we want to do is we want to create this cat state this way, but then do some checking. So in this particular example, it turns out to be sufficient just to have one more ancilla and compare the first and the last qubits. If you work it out, it turns out the only way you can actually get 2 errors in here is if the first and last ones will end up being different. And the reason I mean that is because, if you have a bit flip error that propagates to all 4 qubits, then it's not actually an error anymore, right? Because 0, 0, 0, 0, 0, 0, 0 plus 1, 1, 1, if you flip all 4, you get the same thing. Okay? And actually the same if it propagates to 3 qubits, because then it's equivalent to 1 qubit being flipped. OK, so then by bringing in this extra ancilla, you do these C naughts and check it. But of course, this is, again, something non-transversal. Do we have to worry about that? No. Why not? Well, there's 2 reasons. So one is an error down here can propagate to a phase error up here. But a phase error up here is just not something we can handle anyway. Right? If there's even a single phase error, that changes 0, 0, 0 plus 1, 1, 1 to minus 1, 1, 1, 1, which, remember, is already enough to switch even to odd. OK, so the measurement outcome will be wrong already. So we don't have to worry in that case about propagation. And moreover, the phase errors up here, actually, this is maybe more important. The phase errors up here don't propagate down here. It's the bit flip errors up here that propagate down here. So we only really care about bit flip errors. And the bit flip errors don't propagate backwards through the C naughts here. Okay, so you could have an error that propagates from here down to here, but then it can't propagate back. Okay. And moreover, if one of these things here has a fault in it, well, that could cause this thing to be wrong. Okay, but and it could also cause an error up here. But the thing is, that's just one fault, right? And that's just one error up here, and that's acceptable. What we want to avoid is one fault that causes two errors up here. Two faults can certainly cause two errors. There's no way around that. One fault causing two errors is bad. Okay, so in this circuit, there's no place that one fault. So one fault can cause two errors, but then we'll catch it, and then we'll say, let's throw that out and try again. Or one fault can cause one error that might still bypass this check, but that's OK. That's acceptable. Yeah?
So why can't the additional, it's a little bit backpropagated error.
Right.
If you have an error on the first zero, and then you have an error, let's say, either on the C naught or
sorry. So you have an error on the first qubit and an error somewhere else. So that's two.
On the last.
So we want to consider circulations where there's just one fault.
Okay, one fault.
Right. And again, we want to show that one fault cannot cause two errors.
So there's an error on the first qubit, then it goes down to the
a pre-existing error, an error that occurred up here.
Yeah, that's it right there.
Yeah, okay. But then these things are working properly, and this, well, first of all, it's just an error on one qubit, so it would be okay. But you're worried about it propagating to this last one, I see. No, but okay, so if it's a bit flip error, it can propagate forward here, but then it can't propagate backwards along this C naught. Okay? And moreover, that situation also will cause us to say there's a problem, and then so we'd be discarding it anyway.
Oh.
Yeah.
So we haven't assumed any memory error.
Well, it doesn't really matter in the analysis here. I mean, if you put in like weight locations here and here and here, those can also be faults. That's
like
doesn't.
If the answer, the fifth one is wrong, then we have to repeat this. But the ones here are staying, waiting for that to be triggered, right?
Yeah. Right. So again, think about our model and the definitions that I put in place. So certainly, weight locations, memory locations can have errors in them. That's definitely allowed. But it still counts as a fault if you have a weight location with an error. Okay? And what I'm doing here is I'm counting the total number of faulty locations. And I want to avoid situations where say, S faulty locations can lead to more than S errors in the code. So now it may be unrealistic if your error correction procedure is really, really, really big to say, oh, well, there's only going to be one fault in that. But for low enough error rates, it will be true. Okay? And at this level, I'm just saying, let's suppose we have at most S faults. To satisfy this definition, this has to be true. Okay? And it has to be true for all S less than or equal to T. And so that includes faults in memory locations, faults in gates, any combination. Okay? Any other questions? Okay, so this cat state preparation allows us to do this measurement without having to worry about propagation anymore. Okay, so that solved I don't remember which I said was first, but that solved one of the problems with this non-fault tolerant measurement procedure. So the other problem, remember, was that a single bit error here could give us the wrong answer. Okay, and actually, again, that's gotten worse. We kind of saw this in earlier examples where we're correcting one type of error, but we're adding more qubits to do it, and so we're creating more opportunities to have that one error. Okay, so how do we deal with that? Well, the answer is kind of simple. We just repeat it. And so to repeat it, we just make another cat state and do the same thing again. Okay? And then do it again and again and again. And after enough times, we'll be pretty convinced that we have the right answer. Yeah, there's a bunch of subtleties involved with how that works, which I'll get into in a little bit. But certainly you can see that if you repeat it 3 times, and only one of those, and there's only one fault in the whole procedure, then 2 of those measurements has to be giving you a good answer, right? The other one could be giving you the wrong answer. And so I'll get into the complications in a little bit. But that's the basic scheme here, is in order to do these things, we use the cat states, we prepare the cat states using some non-fault-tolerant procedure, we check them. Then we do transversal gates to interact them with the data. And then we repeat this procedure multiple times. This also kind of illustrates a fairly standard technique that we're going to be using over and over again, which is using kind of special ancillas in order to do fault-tolerant gates. And what we have to do is, and then once we have these special ancillas, we do something relatively straightforward, usually something transversal, to interact it with the code block. But we have to somehow make those special ancillas. And so we're going to put extra effort into making those special ancillas. And the advantage of that is that we know what, well, there's 2 advantages. One is that we know what ancilla we're trying to get. And so it's easier to check when we know what we're trying to get. And the other advantage is that if we check it and find that it's not right, we can discard it and start again, because it's not something that's very valuable. Okay? And there'll be cases where you don't necessarily want to discard it. It might be better to take the ancilla, and if you figured out exactly what's wrong with it, you can fix it. So that's another variation. And which one? Usually discarding is kind of more tolerant of errors. You can handle higher error rates that way. Fixing it is more efficient. So it's kind of a trade-off that you can do depending on where you are. Okay? So are there questions on this? Okay, so then let's take a 10-minute break. And I'll come back and give you an actual fault-tolerant error correction gadget. Maybe we should resume. So are there questions on what we did in the first half or earlier? Okay, so then let's take this, this thing that I just showed you and turn it into an actual fault-tolerant measurement procedure. So this is known as Shor error correction, because it was invented by Peter Shor, of course. Basically, we've done the hard part so far. So the point is that Shor error correction works for any stabilizer code, and to measure the error syndrome for stabilizer code, you just want to measure the generators of the poly operators, of the stabilizer generators. Sorry. Measure generators of stabilizer using cat states. So if you do this once, you use each measurement. Sorry. So you measure. So each bit of the synchrome corresponds to one generator. And corresponds to. You can do that with one cat state. And suppose you measure the whole synchrome once, and then of course we have to repeat it. So we're going to repeat again and again and again. And so. And then once we've done that many times, then we put together those measurement results to determine the actual synchrome. And then based on that synchrome, we're going to do some error correction. So let me put this down here. So once you've decided on what the synchrome is, you just determine what the corresponding error is and correct it. Yeah?
Sorry, cat states, are they just anything of the form, like all zeros plus all ones?
Yeah, so, yeah. So the one I drew up above is the 4-qubit cat state. And in general, if you have a poly of weight W, you need a W-qubit cat state. Okay? So I haven't actually finished describing the details of the procedure, although I actually described it in as much detail as Shor did in his original paper. But there's already one important subtlety here in how I wrote it, which I mentioned just before the break. So I said we're gonna measure the whole synchrome, each using one cat state, each bit using one cat state, and then we're going to repeat the whole synchrome measurement. But you could have done it a different way. You could have said, I'm going to take the first bit of the synchrome and then repeat that measurement many times, and then the second bit of the synchrome and repeat that many times, and so on. And actually, if you do that, that doesn't work. So why doesn't that work? Well, so this is the subtlety with this measurement bit that I said. So suppose you do that case of 3 measurements, okay? And there's one fault in the procedure. Well, yes, it's true that 2 of the measurements will be correct at the time that they were made. But the problem is that the fault can introduce an error into the code block, and that can change what the correct measurement is. Right? So for instance, up here for the 5-qubit code, suppose we measure the synchrome once. Or sorry, we measure just this bit of the synchrome once. Okay? And then there's a z error on the first qubit. And then we measure this bit of the synchrome again. Well, the value that we're supposed to get has changed. Before we were supposed to get 0 plus 1 eigenvalue. Now we're supposed to get 1 minus 1 eigenvalue. Or if there was already an error, maybe it's the other way around. But the point is that you measured 3 times. The first time was right. It said plus 1. The second time maybe was wrong because of the fault. Might have occurred, in that controlled X gate, which might have messed up, not only changed the thing, but it might also messed up the value of the measurement, in which case it could be either answer. And then the third one is also correct, but it says the synchrome bit is 1, but the eigenvalue is minus 1. So the 2 correct ones actually disagree with each other. Right? So if measuring 3 times, while you do get 2 correct ones, it's not as simple as just taking the majority, right? Because it actually changed in the middle. And so what would that mean if we're measuring the synchrome this way? If we're, say, if we're doing 1 bit of the synchrome and measure, and then next bit of the synchrome, measure. The problem is, suppose there's an error that changes, that's in the code block, that happens after we measure the first bit, but before we measure the second bit, or early on measuring the second bit. The synchrome changes, and maybe the first synchrome bit is not right anymore. It was right when we measured it because we repeated it a bunch of times. But now it doesn't accurately describe the thing. And so instead of getting the correct synchrome, at the end we'll get the first synchrome bit corresponds to the old error, and the second synchrome bit and the third synchrome bit and so on, they correspond to the new error. And so we get this kind of hybrid synchrome that's half of one and half of another. And that might correspond to a totally different error. Okay? So you have to be careful. Now, on the other hand, if you do the whole synchrome measurement, and then there's an error, then the next time you measure the synchrome, that will be correct. And every other time, it will be correct for the new synchrome. Okay? So there's always this possibility that new errors, well, first of all, the new error can mess up the measurement that you're making right then. But it also changes the correct answer for future measurements. Okay? So you have to be careful about this. So the other side of this subtlety is that it's not really completely sufficient just to say I'm going to repeat many times. I mean, if you repeat enough times, sure, you'll be able to work something out. But how many times do I actually have to repeat? And what should my rule be for deciding what the synchrome is? Right? I mean, ideally, we'd like to figure out the synchrome at the end of error correction. But we can't always do that, because there could be an error. Just no matter how many times we repeat, there could be an error in the last measurement we make. Right? And we're never going to be able to identify that one. It's just too late. Right? So we need, but that's OK, because it's just one error. Right? And it's a fault that occurred during error correction. So that one error is not going to mess up these gadgets by itself, if what we're doing is good enough before that. So here's a procedure that I'll suggest. It's not the only thing you can do. It's something that's relatively straightforward, though. So you repeat this full synchrome measurement t plus 1 squared times. And then we're going to look for repetition of the same synchrome t plus 1 times. And then if there's no such thing, then just use synchrome repeated the most. Okay, and so once I have this synchrome, then we will determine the error based on that synchrome. Okay, so why is this a good thing to do? So suppose we have this situation where you have up to t faults. Okay, and let's take the extreme case where there are actually t faults. So we know that if you have any synchrome that's repeated t plus 1 times, that one of them has to be correct, right? There can't be, one of them has to have one of those synchrome measurements has no faults in it. Okay, and so that one is correct at the time we see it. Okay, so that's a good thing. So that means that the synchrome that we use in this case will be a valid one, and then we can valid at that time, and then so it's kind of reasonable to act based on that. So how many times do we have to repeat to make sure that that happens, right? Because if we do this one, well, maybe the one that's repeated the most, it's less than t plus 1 times. It might be wrong. Okay. So I can say repeated t plus 1 times in a row. That's my rule. So how many times? So I don't want to have to use this case. I just put it in so that it covers all the possibilities. So how many times do I have to repeat in order for this to be true? Well, suppose I have a synchrome that's repeated t times because there's no faults. We have a situation where we measure t times and there's no faults. And then the t plus first time, there is a fault. Well, that causes some totally different synchrome. And moreover, it changes the synchrome. So the next time we repeat, which is the t plus second time, it's a different synchrome than the first time, or than the one that we just measured. Okay? And then again, we could go for t times, and that could happen again. Okay? So we could have so we have a run of t correct ones followed by one wrong one. So that's t plus one wrong ones. And every time we do this, it requires just one fault for this pattern. And so we could do this t times t plus 1 times. OK? And then at the end of that, we've run out of faults. We've used up all the faults we can have. There's been t faults already. And so if we measure t plus 1 more times, they'll have to all be the same and correct. OK? And so that's a total of t plus 1 squared times. Then we're guaranteed, if there's at most t faults, that some syndrome will be repeated t plus 1 times in a row, and that syndrome will be correct at the time it happens. Yeah?
So if like the first t plus 1 times it's the same syndrome, should we just correct it there then end this?
Yeah, so that's a reasonable alternative procedure where you say, I'm going to...
t plus 1, you get it in a row.
Yeah, so you can just say, I'm not going to, this one I said I want to repeat a fixed number of times that's invariant and always the same. You could just say, I'm just going to repeat, 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 and once I get t plus 1 in a row, I'm going to stop. That works too. I did this partly because even in that circumstance, it's interesting to know what the upper bound of the most number of times is. The other thing is that the procedure that you've described, if there happen to be very many faults, won't ever end.
Oh, I mean like limiting case. So you can...
Well, you could say, yeah, right. You could say, I'll do this until I get to t plus 1 squared times, and if it hasn't happened, then I'll give up. That works too. And so then the third reason, another reason to do it this way is a little more subtle, which is we have many blocks of the code in this whole computer. And we're doing error correction on all of them at the same time. And so if we do error correction on one of them and it ends very quickly, but the other ones are still going, one of them, is going to take a really long time. And the other ones just have to kind of sit around and wait during that time. And so they'll be accumulating errors during that time as well. And so that's not fundamentally a problem. It doesn't kind of change any of these properties or change the arithmetic. But actually, if it's going to have to wait around, you sort of might as well continue to measure the syndrome on it. Because then you'll have, it's better to use, in this circumstance, so I said I wanted to use the last syndrome that's repeated, right? Because that's the one that's most up to date, right? So if you get t plus 1 repetitions at the beginning and then again at the end, either one of them would work. They were correct at the time that you measured. But the later one is probably better to use. Okay? And so that's why I don't necessarily want to stop measuring on these early ones early, on these ones early, even if I got t plus 1 in a row, because maybe I can get more up-to-date information by continuing to measure.
So like just...
It's not totally clear if that's the best thing to do, because you are doing more gates, and that creates more opportunities for errors than waiting. Particularly if storage has low error rates, then maybe that's not wise. But it's also not clear that the other way is better, right? So, like I said, this is not the only way. And I think for specific codes, certainly you can come up with repetition procedures that are better than this. I should say that this is pretty much moot anyway, because the short error correction procedure is pretty inefficient. And so you almost always want to do something else. OK? Other questions? OK, so this procedure is, in fact, a fault-tolerant error correction procedure. So how do we show that? So let's do the ECRP first, right? How do we know that if there's at most S faults, or in the extreme case, well, S faults, that the output state will have at most S errors? Well, the argument that I just gave you said that for S less than or equal to T, the syndrome that we're using was correct at the time that it happened. Okay? And we know from our analysis of this cat state measurement procedure that each fault can only add one error to the code block. Okay, so it could be the S faults happen after the block of t+1 that we're using. Okay, but that means that the error that we correct is the one that was true at the time we get this t+1. Okay, and we get rid of it, and then S faults happen later. And so that's an example where we're going to have actually S faults left over. Or sorry, S errors left over. Okay, but that still satisfies the ECRP. Okay, now it could be some of the faults are before, but that's okay. Then when we measure the syndrome, we're correcting those faults as well, the errors produced by those faults as well. Okay, so this is the point, that by picking a correct syndrome, we're correcting all the errors that existed up to that time, whether they were pre-existing to the error correction cycle or caused during the error correction cycle. Okay? Okay, so that's the ECRP. So what about the ECCP? So the ECCP says we have at most R errors coming in, and we have S faults during the procedure. So again, the syndrome that we pick is correct at the time that it happens. And up to that point, we can have had at most S faults in the circuit because that's all there is. And R plus S is less than or equal to T. Each fault is adding one error, so we have at most T errors in the thing. We pick an error syndrome that's correct at that time. And so we're getting rid of those errors. Now again, there could be more faults that are occurring after, but they're going to be less than T errors from those faults. And therefore, the ideal decoder after the procedure will correct those and give us the logical state. And at no point in this procedure was there an opportunity for logical error. We never accumulated more than T errors. Okay? So the ideal decoder before the procedure gives us the same state. So it satisfies the ECCP. Okay? So that's an actual fault-tolerant error correction gadget. So any more questions on that? Yeah.
So this is assuming that, for example, like we've made the measurement falter in a different way, right?
Sorry, we've made the measurement. No. These are physical measurements, right? That are implemented using that kind of circuit.
We still have to do syndrome measurement, right? So those.
No. How am I doing the syndrome measurement? I'm doing the syndrome measurement this way. I'm going to measure. I'm going to say what are the generators of the stabilizer? Those are these polys. And to measure the first bit, I look at the first generator. And I make a cat state, and I do controlled polys. So I do that whole thing. And then I measure the second bit the same way, the third bit, the fourth bit, till I get the whole syndrome. Okay? And then I repeat that t+1 squared times blah, blah, blah. Okay? So this procedure, I filled in, except for the details of exactly how you check really big cat states, which is hard. You do it by a bunch of similar things. This procedure, I've filled in all the details, right? I've told you what all the circuits are. I haven't hidden anything and assuming anything is perfect, or you make states that come out of nowhere, anything like that. Okay? And that's important because certainly it gets a lot easier if you can assume certain things are perfect or that you can make whatever ancilla state you want. As we'll see. As we get more complicated ancillas, you'll see they can do great things. But you still have to make them. Okay? Okay, so now I want to use the same ideas. I really would like to keep all these boards up, but OK. Actually, I'm going to put them over on the other side. So I'm going to use the same ideas to make a fault-tolerant measurement procedure. So again, for stabilizer code, now we want to measure a logical poly, right? Which, again, can be represented as an X bar, Z bar operation, just as a tensor product of polys. It has some coset of the stabilizer. And so we just have to measure the eigenvalue of that thing. OK? So if we're not being concerned about fault tolerant, again, it would just be that same thing up there in the corner. But with fault tolerance, again, it's more complicated. We're going to have to use these cat-say things, and it's it's actually even more complicated in some sense than the Shor error correction. So I call this Shor fault tolerant measurement. He actually didn't describe this explicitly, but it kind of follows from the Shor error correction procedure. So so the first step actually is going to be to do Shor error correction. And so you want to do the whole thing. You want to do all the repetitions. And yeah, well, OK. I'll explain why in a minute. So now we want to measure some logical poly. So that's represented by P. OK. And then I'm going to repeat these things. So I'm going to do error correction again, and then I'm going to measure this poly. Then I'm going to do error correction again and measure this poly. And I'm going to repeat a total of 2t plus 1 times, taking the majority. So if t is 1, I repeat 3 times. And then this outcome, it's a poly that we're measuring, so it has only 2 possible outcomes, 0 and 1. And so one of them has to be repeated at least twice, and I'm going to take that one. OK, so why do I need to do it this way? Why can't I just measure this and skip step 1 and just repeat step 2, 2t plus 1 times? Well, again, it's this issue about errors changing the eigenvalue. But it's a little bit worse here, right? So before, we were thinking about error correction. And we wanted to figure out what the error syndrome was, and we just wanted to make sure it just didn't keep changing. Right? We wanted an error syndrome that was correct at the time. But the problem is that a single physical error can also anti-commute with the poly that we're measuring. So suppose, again, we're working with a 5-qubit code. The logical z is zzzzz. That's the representative. And we have a bit flip error on 1 qubit that will change the eigenvalue of zzzzz, even though it's a correctable error. OK? So suppose we measure this zzzzz 1 time, and then the second time there's a bit flip error. And so that changes the eigenvalue from +1 to -1. I don't mean it changes the result that we got in the measurement. I mean it actually changes the eigenvalue of the state. Okay? So now we get two things that tell us eigenvalue -1, the second and the third one. But that's wrong, because the x error is correctable, and if we were to correct it, we would get back to the original thing of +1 eigenvalue. Logical 0. Okay? So in order to avoid that, we have to do error correction. And we have to do it every time. Okay? So first we do error correction at the beginning to get rid of any pre-existing errors. And then we make a synchron measurement procedure. And then, because there could be a new error that occurs, we have to do error correction again to get rid of that error. And then do another, not a synchron measurement, a P measurement. Okay? And the point is that by doing error correction separately every time, we can decorrelate errors that occurred. Otherwise, if we get one of these single qubit errors, it'll affect us every time we measure P until we do error correction. Okay? So now let's think about how this satisfies the MCP. So the MCP says we have R pre-existing errors and S faults during the measurement procedure. Okay? So good. So we started out by doing error correction. R plus S is less than or equal to T, so R is certainly less than or equal to T. So the error correction, well, the error correction sub-step will get rid of the pre-existing errors. Now, there could be some errors during the error correction procedure, right? And those could come out those could come out at the end of the error correction procedure. So it could still be that we have errors that go into this cat state, the cat state measurement, the first time we do it. But they're only errors that occurred during this gadget itself, the error correction subpart. Okay. But if there's no errors here, then if no errors during the error correction step, no faults during the error correction step, then and there's no faults during the cat state step, then the measurement output is correct. It's actually giving us the eigenvalue of the logical thing that we're measuring on the logical state that we would have gotten from an ideal decoder. Because basically we did an ideal decoder, right? Or at least an ideal error correction. Just happened to be ideal because there were no errors. Okay? And then the next time we do this, the same logic applies. Any pre-existing errors from the previous step are wiped away, and we only have to worry about new errors. And so if this error correction procedure, again, the second time has no errors, and this cat state measurement procedure has no faults, then the measurement we get is correct that time. And so on and so forth. And if the total number of faults is less than or equal to T, well, then if we look at how many of these step 1 and 2s combined have faults in them, there can be at most T of them, which means there have to be at least T plus 1 that are correct. And therefore, those T plus 1 give us the correct thing. That is, the measurement that we would have gotten if we did it on the ideal state. OK? And so that's why it satisfies the MCP. Any questions on that? Yeah.
Should we repeat the cat state measurement a few times before we do the error correction? Would that help?
No, it wouldn't help. Okay. And the reason it wouldn't help is what I said. Is that so? I mean, it helps against errors that occur in the ancilla that cause us to get the wrong thing. But it doesn't help for an error that ends up in the data block, right? Because then we're getting the wrong answer, even though all the gates in the cat state, even though the cat state procedure itself has no faults. Okay. And so that won't let us, say, repeat fewer times or do fewer error corrections or anything like that. So, I mean, again, you can imagine that for some probabilities, it might turn out to be a little bit better, but it doesn't. The procedure will be bigger, and it's not gonna help you definitely. Not definitely gonna help you. Let's put it that way. Okay. Any other questions? Okay, so let me squeeze onto this board one more thing. Which is the short method of state preparation. So I want to make the logical zero state. So the trick here is that the logical zero state for stabilizer code is a stabilizer state. And in particular, it has its own stabilizer that uniquely specifies that state. Which is the original stabilizer along with the logical z for the original stabilizer. Or if you have multiple encoded qubits, z1, z2, z3. Okay? And so how do I make this state? Well, I do error correction. So now I'm including z bar in the stabilizer that I'm doing error correction for as well, right? So this Shor error correction procedure, which is behind, so this thing here doesn't depend on having any logical qubits. I can do it as well, just as well for a stabilizer state as for a code, right? And then if I do the correction at the end, then if there's at most S faults during this error correction procedure, then the state that comes out has to be a code word, which means it has to be the logical zero state, since that's the only code word, with at most S faults on it. Okay? And notice I can do this on any input state. I don't have to try to make a logical zero and then do this. I can just do anything, take all zeros or random state. And the point is that we're projecting on some Pauli error relative to the zero, the logical zero, and then I correct that Pauli error, okay, or my best approximation to it. And so that means that, and this was true, remember, regardless of the input. So I take whatever input, I do the error correction, I get the output, which is a code word with at most S faults. And if you look up there, that's exactly the PPP. Okay, I'm getting the logical zero with at most S faults. Or I'm getting the code word with at most S faults. And it also gives us the PCP, right? Because it has at most S errors relative to the logical zero. And so if I did an ideal decoder, I get the logical zero, definitely, or the decoded zero, the ideal zero. Okay? So this is a fault-tolerant state preparation procedure. Okay? So this gives us, well, not quite a complete set. So we have we have transversal gates. We have a bunch of logical gates, at least for the 7-qubit code that way. We have state preparation. We have measurement. And we have error correction. So we have examples of all the different kinds of gadgets, at least. But as I said, these Shor error correction procedures are a pain in the neck. And the measurement is even a bigger pain in the neck because you have to do 2t plus 1 error correction procedures as a subroutine, as subroutines. So we'd really like to find better ways to do these things. So before I do that, I want to make sure there's no more questions on these Shor procedures here. OK. So the next thing I'm going to do then is, so those things are nice because they work for general stabilizer codes. And they're kind of very general and very flexible. But they are inefficient. And also, I mean, they're fault tolerant, but because they're so big, there's a lot of opportunities for errors to occur. And so you need lower error rates to make sure it's actually true that you have at most t errors during the gadget. So I like smaller things. And I'm going to do that by specializing to CSS codes. And so the first thing, when we deal with CSS codes, the first thing we can simplify is the measurement procedure. And we can simplify it a lot. In fact, it's really, really easy for CSS codes. So why is that? Well, so CSS code, remember, has a stabilizer that's formed from two classical codes, right? The Z's are from one classical code, and the X's are from the other. And the code words look like this. This was a code word corresponding basically to a logical V, where V is in C1. Okay? So two different V's in C1 gave us the same code word if they differ by an element of C2 perp. Right? So we're breaking C1 into cosets of C2 perp. And those are corresponding our different logical states. So now suppose we have a bit flip error. E. And so E is going to be a bit string. Bit string which is 1 where there's an error. So this is like what we did when we were talking about classical error correcting codes. And it's 0 where there's no errors. So suppose we have this bit flip error that's affecting potentially multiple qubits. And we have a code word. So what's the state now? Well, we have still sum over W in C2 perp. But instead of V plus W, we have V plus W plus E. And suppose we take the state and measure every qubit. That's going to be our fault-tolerant measurement procedure. So this is going to measure the logical Z. So when we measure every qubit, what do we get? Well, there could be some faults during the measurement procedure itself, but let's ignore that for the moment. What we get is V plus W plus E for some random W in C2 perp. Okay? But remember, C2 perp is a subset of C1. So V plus W is in C1. It's a code word. And C1 is an classical error correcting code. So if we get something of this form, we can use the classical error correction properties of C1 to get rid of that error. And then we'll get back to V plus W. And that, remember, is again some element of C1, but it's an element of C1 that corresponds to the same logical value here. So this gives us the logical output. Right? So for instance, for the 7-qubit code, we have just one logical qubit. The code words are elements of the classical Hammond code. C1 and C2 are both the classical Hammond code. And so what we're going to get, if you write it out, is you get basically the even elements of the Hammond code correspond to the logical 0. And the odd parity elements of the Hammond code correspond to 1. So the way this works is you measure everything. You get some bit string. Since it might have errors in it, it might not be a code word. But you do error correction for the classical Hammond code. You get back a code word of the classical Hammond code. If it's an even weight, you say logical 0. If it's an odd weight, you say logical 1. OK? So why does this work? So we want to show that it satisfies the measurement correctness property. So suppose we had at most R errors coming in. So that means that this initial E that we have is weight at most R. If there's phase errors coming in, that doesn't matter at all, because we're just going to measure, and the phase just disappears. OK? So it's only the bit flip errors that matter. And of course, there might be additional faults that occur in the measurement steps. But since we're measuring each qubit separately, each single qubit measurement, that's one location. So as faulty locations, they can only affect those specific qubit measurements. OK? So instead of V plus W plus E, we'll have V plus W plus E plus F, where F is a bit string that's 1 on the faulty measurement locations. And E plus F will again, well, E has at most weight R, and F has at most weight S. So E plus F will have weight less than or equal to T, because R plus S is less than or equal to T. And therefore, the same argument says that the error correcting code, assuming the distance of C1 is big enough, can correct that error. OK? So if it's a non-degenerate CSS code, then the distance of the code will be, at most, the distance of C1. And so we will be able to correct that E plus F. We'll get back a code word, and then we can deduce the coset from that, which is the same thing that we would have gotten if we just did the ideal decoder. Right? Because this is what we would have gotten from the ideal decoder, V plus W. OK? So now there was a little caveat on there. I said if it's a non-degenerate code. So what happens if it's a degenerate code? Let's work that out. OK, so it could be, if we have a degenerate code, that the distance of the quantum code is actually greater than the distance of C1. Remember, an example of that was the 9-qubit code. So suppose that happens. So that means that we have so it means we have a bit flip error that has weight less than D. So S is less than D. And so we have some error E with weight S. But S is, less than, but it's greater than D1, which is the distance of C1. Actually, maybe I should do something other than S. What's so good? Let's call it M. Okay, and the point is that E has the property that so if X is in C1, then X plus E. Well, okay. I guess all I really need to say is that E is in C1. Is that what I want to do? Sorry, hold on for a second. Oh, yeah, sorry. So, but the point is that because the distance of the quantum code is D, and this has weight less than D, it still is a correctable error for the quantum code, right? So how can that be, since it's not detectable by the Z code? Well, the way it can be is that E is actually in C2 perp. No, sorry, that's not right. E is in no, yeah, that's right. It's in C2 perp, right? So what that means is that it's in the stabilizer. The corresponding bit flip error is in the stabilizer, okay? Which means it's coming from C2 perp. Okay, so we have some situation where we have two errors. We have X plus F is equal to X prime plus F prime. And therefore, F plus F prime is one of these situations where it's in the code, and so it's in C2 perp. And so down here, what we would get is instead of V plus W plus F going to V plus W, we instead get it to V plus W plus this F plus F prime. Okay, people are confused. So let me try this argument again. So what's the situation that we're worried about? We're doing here, we're saying, okay, we have V plus W plus, now I've called it F. It's probably not wise, but I changed the letter. We have V plus W plus F is the actual error that we have. But we don't know what VW and F are, right? All we know is we have some bit string. And we want to deduce what V plus W is and what F is. So we apply the error correction procedure from C1. But this actual F is bigger than the distance of C1. So we're not necessarily going to get it right. Okay? So instead of F, we might think it's F prime with some different X prime. Okay? But in order for some code word plus F to be equal to some other code word plus F prime, well, the quantum code is still correctable. And that's what this argument was saying. And that means that F plus F prime has to be has to be something that's in the stabilizer. So it has to be in C2 perp. Okay? And so So suppose we think that it's f prime instead of f. Well, then what we're going to do is we're going to add f prime. So to get this, we would normally say we'll add f. And so we get v plus w. But instead, we're adding f prime. So this is what we get instead. OK? And, well, this is in C2 perp. This is in C2 perp. And therefore, these two together are still giving us the same coset as v. OK? And therefore, the logical thing that we get out is the same as we would have gotten from the ideal decoder. OK? So even when it's a degenerate CSS code, this is still a perfectly good fault-tolerant measurement procedure. OK. So I have time to do this. OK, are there questions on that? OK. OK, so you see that measurement procedure is way easier than this thing that I'm erasing now. So if you have a CSS code, actually, this is a good reason by itself to use a CSS code. You don't have to do this. You can do that. But there's another good reason, which is that you can also make a better error correction procedure. So that's the next thing I want to tell you. And so this is called Steen error correction. OK, so how does it work? So remember, I mentioned last week that for an arbitrary CSS code, the C0 is a valid transversal gate. Right? So if you have any two blocks of a CSS code, you can use transversal C0, and it'll do the C0 between the logical qubits. OK? So we're going to take advantage of that to design an error correction procedure. On the face of it, that seems a little bit silly, right? Because we don't want to change the logical state for an error correction procedure. But it turns out that, that you can still do it. And the way you do it is you're doing a C0 between an ancilla qubit, a logical ancilla qubit, and the code block that you're interested in. And so in particular, yeah, OK, I see. So in particular, let's start out with a variant of this measurement procedure that will do a non-destructive measurement. OK? The measurement gadgets that I talked about are destructive, but it's sometimes interesting to be able to make the logical poly without decoding. Right? In this case, it was definitely destructive. We measured all the qubits. They're gone. The Shor error correction procedure that I erased was actually non-destructive. Right? So let's do something similar for CSS codes. And then we'll modify it to turn it into an error correction procedure. So how does that work? Maybe I could start to use this. So what I'm going to do is I'm going to take two code blocks, but one of them is going to be a logical 0. And this is the code block that I want to measure. And then what do? Well, I do the C0. And by this green C0, I mean the transversal C0. OK? And then I do a measurement of the ancilla block. OK? And this measurement is, again, transversal, done according to this procedure. OK? And then, so by the argument that we already have, this thing satisfies the MCP. This thing is a transversal gate, so it satisfies the GCP and the GPP. And this logical 0, let's assume we made it in a fault-tolerant way, maybe with this Shor method. Okay? So creating it also satisfies the PCP and the PPP. Okay? So now let's put those together. Well, suppose we have at most R errors coming into this state, and at most S faults somewhere in these 3 gadgets. Well, yeah, OK. So maybe this is a good time to show you how these gadgets can kind of chain together. So we have here a gadget, a measurement gadget, and then we have a gate gadget. Sorry, a preparation gadget, and then a measurement gadget. So suppose we have, as I said, R errors coming in, and we have S1, S2, and S3 faults here. So we don't really care at the moment about how many faults we can get output here. What we care about is whether we can replace this with an ideal thing. So first we can apply the PCP here. Well, actually, no. First I want to apply the PPP. I'm going to need more space for this, I can see. Well, I'm going to try to squeeze it in. OK. So first I'm going to apply the PPP. And so the PPP lets me take this, this state preparation gadget and insert a filter. So this is equal to this. So then I want to apply the GPP that lets me push these filters through the gate here. And so that's telling me that I have this. And here I could have R plus S1 plus S2. Although, again, I don't really care about that. Here I could have R plus S1 plus S2. And I do care about that one. And then here I have S3. OK? And then this thing here looks like the thing that appears on the left-hand side of the MCP. OK? So this is equal to this. Oops, and I need the red. Well, OK. I guess I could have had the reds all along. OK? So you see that? And now is when I really wish I had more space. So now I have this ideal decoder. The problem is I have these filters in here. But I can get rid of them by, again, using it's behind. But you see, I have the gate propagation property up there. And so if I use it backwards, I can take this thing with filters before and after and just erase the ones after. OK? Then I have the situation that looks like the gate correctness property, where I have filters, gate, and then ideal decoders. And Yeah, this is actually maybe a slightly difficult application because I only have one ideal decoder. So I'd have to stick in another ideal decoder here in order to make this work. And then I can push the ideal decoders back. And then what I get, well, I'll try to squeeze it in here. Ideal decoders on both of these. And then this ideal gate. And then the ideal measurement. OK? And then you do the same thing. You get rid of this filter using the PPP backwards. And then I use the PCP backwards to push this ideal decoder back to the preparation. And what I get at the end is basically this. Right? Along with this, this thing here. So basically, I'm just doing this circuit on the ideal state. Okay, and what does this circuit do? Well, it's just a non-destructive measurement procedure, right? It copies it in the z basis, and then you measure it. And along the way, so the first thing I showed you was that, well, OK. And so along the way, what I've done is I've shown you that this satisfies some non-destructive version of the MCP. But I also showed you that it satisfies some sort of propagation property that I didn't write down because I didn't write down a non-destructive measurement thing. In that this output state has at most R plus S1 plus S2 errors. Okay. Anyway, the upshot is that this procedure is fault tolerant as well because I've chained together 3 fault tolerant things. And it gives me the logical measurement of the z for this thing while leaving the state around. Okay? So let's look at this and understand how that works. Well, when we make this measurement here, we're getting a classical code word because it's a CSS code. But it'll be a classical code word with errors in it. And there are bit flip errors that correspond to errors that occurred during the measurement. There could be errors that occurred during the C0, faults that occurred during the C0. There could be faults left over from the state preparation. But what else could there be? Well, suppose there's a pre-existing error up here, a bit flip error. Well, it would have propagated along this C0 and ended up down here in this thing here. That's why this filter here is an R plus S1 plus S2. Right? It's getting errors that were pre-existing in the state. Okay? So what I'm getting here is a classical code word that has errors from the faults that occurred in the circuit, but also the pre-existing errors. Okay? So that's something that's cool. That's going to be a way that we can look for bit flip errors that were already there. Now, you don't actually want to do this circuit because you do it and you're doing a logical measurement. That would change the state. So that would definitely violate the ECRP. Sorry, the ECCP, because it wouldn't be correct. It wouldn't be implementing it would be implementing something non-trivial. It's supposed to be trivial. Right? So we don't want to do that. But suppose we don't use the 0 ancilla here. The 0 ancilla let us copy this information and then learn it when we made this measurement. But suppose we instead do the plus ancilla, the logical plus. Okay? Now, what does this do? If you think of the decoded version of this, what does it do? Well, if this is a 0, nothing happens. If this is a 1, this gets flipped, logical bit flip. But for plus, the bit flip doesn't do anything. So the decoded version of this circuit is just trivial. It doesn't, you're not getting any information. But the encoded version, what you're getting out here, so you're not getting information. So what is this? What is the output here for the decoded version? It's equally likely to be 0 or 1. And for the encoded version, this is a random code word of C1. But it has bit flip errors because this is not perfected. And what are those bit flip errors? What are those bit flip errors? Well, they're bit flips that come from faults during the circuit. But they're also bit flip errors that came from the code word that we put in at the beginning, the quantum code word. OK? And so that's giving us some information about what those bit flip errors are. OK, so actually, I'm going to claim what I want to do is I just want to correct those bit flip errors without doing anything else. So you could repeat this procedure, do this measurement a bunch of times, and then you'll get some different sets of errors, and you'll say, oh, the ones that are consistent, those are probably the pre-existing ones. The ones that change every time, those are just from faults that happened along the way. But it turns out that doesn't really matter. You don't really need to do that. And the reason is kind of interesting. So let's describe these bit flip errors as E, which are broken down into F plus G. So these are, you're going to have to break it down even more to really make the detailed analysis, but this will be enough for the level that I want to do now. So the F is the pre-existing bit flips, and G is from faults in the circuit. OK? And so I started out with the code word that's sum over W in C2 perp, V plus W plus F. And now I'm correcting it by E. And so now I have sum of V plus W plus F plus E. But F plus E is G. So what I have out here is V plus W plus G. So I've gotten rid of the original errors, but I've introduced new errors that corresponded to the bit flip errors that occurred somewhere in here. OK? And the point is that there's at most S faults in this part of the thing. So that means that at the output here, I have at most S faults, which is what we've asked from the ECRP. OK? And that was true no matter how many errors were coming in, no matter what the weight of F is. Well, OK, that's not quite true. So again, you have to make a more careful argument. So if the weight of F is very large, we're not actually going to be able to deduce F plus G because it'll be bigger than the distance of the classical code that we're dealing with. We'll get F plus G plus some code word. But that code word, again, will just switch us to some different. In the case of the ECRP, there could be many, many errors. We don't care if the logical state is right or not. OK? So we might be switched to even to a different coset of C2 perp. But that's OK. It'll still be some code word plus G in the end. And so that's at most S faults. Now, you need to be a little bit careful here. Because I kind of, this is what I'm saying, that you actually have to subdivide it a little further. So the problem is that I've assumed that the only way faults could get up here, new errors could get up here, is from this, when I try to correct using the wrong things. But that's not true, right? These C-naughts, they can have faults that could affect here. And errors from here could propagate up here. But, and this is the part that's interesting, that doesn't matter. And the reason it doesn't matter is because this is a transversal gate. So suppose there's a fault in one of these C-naughts that caused an error down here, but it also caused an error up here. This might be a Z error, whereas this is a bit flip error. So they're not going to cancel out, but they're on the same qubit, right? And similarly, for any error that propagates up here, it's going to be on the same qubit as anything that shows up here. And so while I can also have phase errors, additional phase errors that have been created by this procedure, and I haven't shown you the phase error correction part of this yet, they will be on the same qubits as G, and so the total weight of the error will still be at most S. Okay? Okay, so then this is the bit flip part. And then the phase part, I'll just stick it over here, is the same thing, but basically in the Hadamard basis. So what do? We have this thing. Now we do use the logical zero, but we do the controlled knot the other way. Transversal controlled knot the other way. Since this is a logical zero, this doesn't do anything if there's no errors. If there's errors, the Z errors can propagate backwards along the C naught. And so we have phase errors here, and so we do the Hadamard and then measure. And again, we deduce the classical, the error from classical error correction. But this time it'll be the phase error. Okay? So the Steen error correction procedure actually consists of doing one of these and then the other one. And then you take those two synchromes, you correct bit and phase flip errors. And as I said, no matter what comes in, the thing that comes out will have faults just on the qubits corresponding to the S1 things here and S2 things here that happen to have faults. Okay? So we do satisfy the ECRP. And so then the ECCP, which is again hidden, the ECCP says, suppose we do have at most R errors coming in, and we have at most S faults during the procedure. And then we do an ideal decoder. Well, so in that case, the total number of errors that we're dealing with is at most T. And so in particular, the number of bit flip errors is at most T. Let's assume the non-degenerate case, it's a little bit easier. So the classical error correcting code is actually getting the correct E here. But it still has this F plus G. But that means that this thing that we hear is actually V plus W plus G, which is the correct coset plus a small error that the decoder will get rid of. Okay? And therefore, the ECCP is satisfied as well. Okay? So yeah, you can see that this is a lot better than Shor error correction. You don't need to repeat it. And even just one implementation of it, one repetition, even if you didn't repeat the Shor error correction, this would still be better, because the Shor error correction procedure requires, this whole separate cat state thing for every bit of the syndrome. Whereas here, all we're doing is transversal C0s, twice, and then some transversal measurements. And this Hadamard, I should say, so for the 7-qubit code, the Hadamard is also a transversal gate. For some other CSS codes, you still want to do the transversal Hadamard here. So then it might not take the code to itself because it switches C1 and C2. But that's actually what we want here, because in this case, we're measuring a code word of C1. In this case, we're measuring a code word of C2 in order to do the phase error correction. But anyway, the point is this only involves transversal gates. So what we have to do in this circuit is much less. Except that we still need to make these logical zeros logical plus states. So let me very quickly show you another way to make those. I mean, you can still make them using the Shor error correction procedure, and some people would advocate that. But actually, it's a little bit easier to make them this way. So, what I would suggest doing is if you do some non-fault tolerant circuit to create these logical zeros, and then do this circuit here, well, if one of these things has a fault that changes the logical state, one of these non-fault tolerant encoders has a fault that changes the logical state so that it's a logical 1, then what we'll get out here is a 1, a logical 1. And then we know that there's a problem, and so we can discard it and try again. Now, of course, if both of them have errors, then that doesn't work. But that means, but since these are separate non-fault tolerant encoding procedures, that requires 2 faults. Okay? And so usually, if you're dealing with a code that just corrects 1 error, this is easier. Now, what happens? Now, I mean, you might worry. What happens if there's a phase error? Right? I mean, obviously, we could have an error that just affects 1 qubit. That's fine. But if we have a phase error, and this is a non-fault tolerant gate, it could be a logical phase error. But this code word is supposed to be a logical 0. There's not really such a thing as a logical phase error. Again, if you're dealing with a code that corrects that, well, if you're dealing, say, with the 7-qubit code, then this is perfectly well defined. There's a 1-qubit phase error, and there's a logical phase error, and there's nothing else. You could have to worry if you're dealing with a code that corrects multiple errors, because then you could have one fault in the circuit give you a 2-qubit phase error that's not a logical phase error. And then you have to do something similar, but in the Hadamard basis, to detect logical phase errors. Well, to detect multiple qubit phase errors. That's the other thing, is this is also an error correction procedure, right? So if you're dealing, so if, again, if you have a code that corrects multiple errors, then you can say, well, if there's too many errors here, I'm going to discard it. Or really, if there's any errors, you might as well say, I'm going to discard it. Okay? And so it could be, again, if you have a code that corrects multiple errors, that you have one fault that's causing 2 errors, but not a logical error. And that's still bad, right? You still want to avoid that. So that's why you should do that. But again, if you have a code that corrects multiple errors, T is larger, there's possibility of 2 faults. And so you could really do C0s to multiple things, do multiple checks like this. So this becomes more elaborate. But at least for the 7-qubit code, this is all you need to do. And this is usually a much better way than going through the whole short error correction procedure. Okay? So this is an alternate logical 0 protection preparation procedure. Okay?